Are you tired of taking derivatives of polynomials? Do you want to take your derivative game up a notch to impress your friends and loved ones? Well, let me introduce you to an old friend of mine. The product rule. So as its name implies, the product rule is used to take the derivative of functions that are the product of other functions, f of x times g of x. The product rule states that the derivative of this product will be f of x times g prime of x plus f prime of x times g of x. Some of us, though, might prefer a more qualitative description of the product rule. So if we label f of x first and g of x second, then y prime will be equal to first times the derivative of the second plus the derivative of the first times the second. All of this might not make much sense to you right now, so in this video we will illustrate the product rule through a few examples, including one with a table. How exciting! Then we will discuss some common mistakes that students often make, take on a triple product rule example as a challenge, and if you survive until then, we will finish off by proving the product rule itself. So our first encounter with our friend the product rule will be x to the third plus 5x in parentheses times sine of x. Let's add some color and joy to this little party. For this parenthetical element, let's color it red and cleverly label it first, while let's color sine of x green and label it second. Now instead of charging head first into the product rule, let's review the derivative of each of these elements. So first we have to take the derivative of this polynomial. We of course use the power rule to take the derivative of x cubed, so we're going to drag down that power of 3 and let it settle in the front of the x, and then subtract 1 from the old exponent to get the new exponent of 2. Next, the derivative of 5x is 5, as the derivative of a constant times x is that constant. Now, for the second function, sine of x, we remember that its derivative is memorized to be cosine of x. You really should just memorize your trigonometric derivatives, since you never know during what dark times you might need them the most. Finally, with these derivatives taken and the stage prepped, we can start the show. The first part of the product rule is just f of x, so we literally just have to rewrite the first function verbatim with no thinking required. Then we multiply that by the next part, which is a bit more spicy because it's g prime of x. Let's retrieve our derivative of the second function, which we already remember to be cosine of x, and place that next to our f of x. Halfway done, we separate the two halves of the product rule with a nice solid plus sign. The third part of the product rule is the derivative that we haven't used yet, f prime of x. So we are going to grab our first derivative from earlier, wrapping it gently with parentheses. And we end the product rule with my favorite part, g of x. So to finish off, all we have to do is copy verbatim the second function, sine of x. And with that, we have conquered our first instance of the product rule. So now it's time for you to take off your little arm floaties and wade into the deep end. Our second question will be to take the derivative of the square root of x times 5 to the x. Pause the video now and see if you can implement the product rule yourself. I certainly believe in you. Okay, let's see what we're made of. We will label square root of x first and color it red, and label 5 to the x second and color it green. Like last time, let's take our derivatives first. Remember that in order to take the derivative of the square root of x, we should rewrite it as a fractional exponent so that we can utilize the power rule, as square root of x is the same thing as x to the 1/2. Now when using the power rule here, some students have trouble with our new fractional exponent in negatives. So take caution that our new exponent will be 1/2 minus 1, which is negative 1/2. careful for this next derivative too, because this term is not x to something, but something to x, where x is in the exponent and not the base, so we can't use the power rule here. Instead, we need to use the a to the x rule, where the derivative of a to the x is a to the x times ln of a, and not ln of x, as some students mismemorize. Thus, the derivative of 5 to the x is 5 to the x times ln of 5. Now that we have all of our original functions and derivatives ready to go, let's try to piece together the answer without explicitly writing out the formula for the product rule again. I like to start off the product rule by immediately rewriting the first function, in this case square root of x, so at least I know I got something right. Then it's derivative of the second, so that's going to be 5 to the x times ln of 5. The middle operation of the product rule is always plus. Next, because we kept the square root of x the same during the first half, we have to write out its derivative now, which we found using the power rule. And to complete the answer, we just copy down the second function 5 to the x with no change. Some teachers believe that fractions are more aesthetically pleasing than negative exponents, which I don't understand, but to placate them, we can simplify our answer as a fraction instead of a negative exponent. Check your work against mine. Did you get the same answer as I did? Let's review some common mistakes that past students have made when applying the product rule, in the hope that we don't fall victim to their past pitfalls. We're going to consider these common mistakes with the example 2 times x squared minus 4x times inverse tangent. Mistake number 1 is the one that makes me the most sad, so if you want your teacher to question their choice of profession, I would suggest this mistake to make. And that mistake is just ignoring the product rule completely. Students will be so excited to announce to the world their knowledge of the derivative of x squared minus 4x being 2x minus 4 using the power rule, and the derivative of inverse tan being 1 over x squared plus 1, that they will completely forget the existence of the product rule, but like you, nobody likes to be forgotten. Mistake number 2 is a little more subtle than mistake number 1. For this mistake, students will correctly remember to use the product rule, so they'll start off with first times derivative of the second plus derivative of the first times the second. But notice that the derivative of the first function is the entire quantity 2x minus 4. So while a student might argue that their answer is correct, technically it is not, as the inverse tangent needs to be multiplying both the 2x and the minus 4. If you don't include the parentheses and were to simplify further, you might think that the inverse tangent will only be multiplying the minus 4, and your teacher, as much as it might break their heart, will be forced to deduct that precious point. Mistake number 3 is even more subtly dangerous than mistake number 2, and involves this little 2 at the beginning of the function. Basically, this 2 or any similar constant will need to be included in both halves of the product rule. Students will start off strong as before, first times derivative of the second, but then after the plus, they will neglect to include the 2 for the second half of the product rule. This mistake is especially prevalent when the product rule is used for implicit differentiation questions later on in your calculus journey. The easiest way to avoid mistake number 3 is to affix our constant of 2 to the first function so that we will not think of the first function as just x squared minus 4x, but 2 times x squared minus 4x. Let's finally find the derivative of this function by navigating around these common mistakes of the product rule. We first recognize that we have a product of functions, so that the product rule is indeed necessary. As we label the first, we include the 2. The derivative of the first according to the power rule is 2 times 2x minus 4 in parentheses. The derivative of inverse tangent can be found using implicit differentiation, but for now we'll just memorize it as 1 over x squared plus 1. Now with the derivative sliced and diced, we apply the product rule. First, which is 2 times x squared minus 4x, times this derivative of the second, which is 1 over x squared plus 1, then the derivative of the first, which is 2 times 2x minus 4, and we are especially conscientious to include both the 2 and the parentheses. And finally, with a deep breath, we rewrite the second function, inverse tangent, and we don't forget to give thanks to those that stumbled before us, so that we may run. Now that we've covered our common mistakes, let's return to a few more examples. It's time to finally table it up. For our third example, we're going to try to take the derivative of this function, x squared minus f of x g of x. Here, as promised, is our table. But before we can use this lovely table, let's take the derivative. As we do so, let's try to avoid some of the common mistakes that we just alluded to when applying the product rule. First, x squared here is isolated by itself, so its derivative is just 2x by the power rule. The second part of our function is a product, so the product rule will again play the hero here. Note that we should include the negative with f of x as our first function, lest we make common mistake number 3, as this negative will eventually be distributed to both halves of the product rule. With the second function being g of x, let's apply the product rule again. It'll be first, which is not just f of x, but negative f of x. Then the derivative of the second is g prime. For the derivative of the first, we still include the negative, so that's negative f prime of x. And we end the product rule with the second, so we simply copy down g of x. We have finished the derivative, but unfortunately we're not done yet. Notice that our answer to this example will ultimately be a number, as we teachers often greedily ask students not just to take the derivative, but also to plug in a certain x value into the derivative, in this case 2. So let's change all of these x's into 2's. Now we finally get to use our beautiful table, as we retrieve from it all of these function values at 2. After 2 times 2, it will be negative f of 2, which according to the table will be negative 3. Then g prime of 2, which is 4. Negative f prime of 2 is minus 5. And g of 2 is negative 1. Two negatives will cancel out, so negative 5 times negative 1 is plus 5. Simplifying further, 2 times 2 is 4, and 3 times 4 is 12. Our last little bit here is 4 minus 12 plus 5, so our final answer to our table question is negative 3. So I threw in this mini example because some students become so enthralled with the product rule that they apply it to every single situation in which there is a product. However, there are some products where an application of the product rule won't necessarily be wrong, but it will be a waste of one's effort and time. Let's naively use the product rule for this example of pi squared times tangent x to avoid committing this little faux pas. As normal, we label pi squared first and tangent x second. Let's focus on the derivative of pi squared, which notice doesn't consist of any x's. This is a sort of gotcha derivative, as you don't take the derivative of pi squared with the power rule, even if pi is being raised to a power, and that's because pi squared is a constant, and the derivative of any constant is 0. The derivative of tangent x can be later found using the quotient rule and the derivatives of sine and cosine, but for now we'll memorize it as secant squared. So if we go for the product rule as usual, it'll be first, which is pi squared, times the derivative of the second, which is secant squared. After the plus, it'll be derivative of the first, which is 0, times the second, which is tangent x. And if I know anything about math, it's that 0 times anything is 0, so this derivative would reduce to just pi squared times secant squared. And that's why applying the product rule here, while not technically wrong, should still be avoided, since we can skip directly to the derivative. While pi squared times tangent x is indeed a product, it is the product of a constant pi squared times a function tangent x and not two different functions. Instead, we should make use of this constant rule for derivatives that you might not be explicitly aware of, but no doubt you've used this rule several times in your calculus journey. That rule states that the derivative of a constant times a function is that constant times the derivative of the function. So going back to our example, the derivative of pi squared times tangent x is just the constant pi squared times the derivative of tangent x, which is secant squared. And by eschewing the product rule for this derivative, let's appreciate how much time we were able to save for bigger and better things. So while we hope to become closer friends with the product rule, we're only going to invite it to gatherings consisting of a product between two different functions. For this last example, we're headed to the big leagues, as we're going to tackle a product rule question that has not one, not two, but three functions. Even if this question isn't really any more difficult than our previous examples, it probably won't appear on the AP exam, but I have seen it on college calculus exams, so we might as well give it a go. Our triple product rule example is x to the 7th times secant x times ln x. X to the 7th is our first function f of x, secant x is our second function g of x, and we finally get to use a third color for ln of x. Purple should serve us nicely for our third function h of x. Let's state the triple product rule for functions of the form f of x times g of x times h of x. Actually, pause the video for a second and just guess what you think the triple product rule is based off the regular product rule. Were you able to guess this? First times the second times the derivative of the third plus first times the derivative of the second times the third plus the derivative of the first times the second times the third. For the sake of consistency with our other examples, before we apply this behemoth of a formula, let's review each of the derivatives of our trio of functions. For the derivative of x to the 7th, we will savor our final application of the power rule for this video, as we drop the 7 to the front and subtract 1 from the exponent to get 7x to the 6th. Later on, the derivative of secant x can be found using the derivative cosine, the chain rule, and the trig properties, but for now we'll just acknowledge it as secant x tangent x. And finally, remember that the derivative of ln of x is 1 over x, which can be verified through the derivative of e to the x and implicit differentiation. Now we just need to maneuver around the pieces of this puzzle for the answer. Our final solution will be first, which is x to the 7th, times the second, which is secant x, then derivative of the third, which we memorized to be 1 over x. A third of the way done, we next have the first function, which is still x to the 7th, times the derivative of the second, which is secant x tangent x, times the third function, ln of x. And we conclude with the derivative of the first, 7x to the 6th from the power rule, the second function, secant x, and we copy down the third function of ln of x. Hopefully after all of these examples, you're now equipped to tackle any product rule question that your teacher may throw at you. For those stragglers who've survived to this point, I salute you, and I offer you the gift of the proof of the product rule as an appreciation for your academic tenacity. With most proofs involving derivatives, we start with the definition of the derivative. Recall that the derivative is by definition the slope of the tangent line, or in math terms, the limit as h approaches 0 of f of x plus h minus f of x over h. If you use this definition for g of x instead, it will be the limit as h approaches 0 of g of x plus h minus g of x over h. Then let's apply this definition a third time to a new function f times g. It isn't any more difficult than constructing the definition of the derivative for f of x. It will still be the limit as h approaches 0, with the denominator of the fraction being h. For the left side of the numerator, we plug in x plus h for both x's that we have, so it will be f of x plus h times g of x plus h. We then simply subtract our function, which is f times g, to finish our fraction, and thus we've completed our definition of the derivative for f of x times g of x. Now our goal will be, through clever algebraic manipulation, we will definitively show that this limit is indeed our good old product rule. To make progress, we employ a trusted math trick, adding 0 in a clever manner by subtracting away a term and immediately adding that term back. So we're going to expand the numerator of this fraction, and by a good deal of tinkering and trial and error, we discovered that we should subtract f of x plus h times g of x, and then immediately add f of x plus h times g of x. So in essence, we've added 0 or nothing to the numerator and thus have not modified the value of the limit at all. Let's examine why we should do such a thing. By introducing terms to the numerator of this fraction without changing its value, we can split this fraction into two fractions at the midway mark of the middle plus sign. Spoiler alert, this plus sign becomes the plus that has dutifully served as the midpoint of all of our product examples thus far. Now let's take the first fraction after our split. What do you notice algebraically about this numerator that we can possibly use to our advantage? Well, because both terms include f of x plus h, we can factor that out, and we're left with f of x plus h times this fraction g of x plus h minus g of x over h. Let's do something similar with our second fraction. Notice that both of our terms of the second fraction's numerator contain g of x, so we factor that out of the second fraction, and we are left with f of x plus h minus f of x over h times g of x. Now with everything separated and factored out, we can apply the limit as h goes to 0 to each successive term. Notice that as h goes to 0, then f of x plus h goes to f of x plus 0, or simply f of x. H going to 0 for the fraction g of x plus h minus g of x over h is precisely the derivative of g of x. So we can replace that entire limit fraction with g prime of x. Likewise, after the plus sign, h going to 0 for the fraction f of x plus h minus f of x over h is by definition f prime of x. Finally, since g of x does not contain any h's, h going to 0 does not affect that term, so it remains g of x. And behold what we've stumbled upon here at the end. Old reliable itself, the product rule. First times the derivative of the second plus the derivative of the first times the second. With that, I hope you've gleaned from this video anything that you could ever possibly need to know about the product rule. And I thank you for spending some time with me and my old friend until we abandon it for the quotient rule.